Today, we're diving into a research paper that really shook things up. It basically asked one simple, kind of terrifying question. What if the entire AI industry was building its most powerful models completely the wrong way? All right, let's get right into it. For years, the story of AI progress seemed to follow this one simple rule. But what if the whole field was just chasing size, scale, when the actual secret to intelligence was hiding somewhere else entirely? Just look at this timeline. It was a flat-out arms race for size. In 2020, GPT-3 hits the scene with 175 billion parameters, which was mind-blowing at the time. But then, right after that, you get Jurassic 1, DeepMind's own Gopher at 280 billion, and then boom, Megatron-Turing NLG blows past the 500 billion parameter mark. The trend was it was explosive. And the thinking behind all of this was incredibly simple. Bigger is always better. More parameters, smarter model. That was it. That was the core belief, the guiding light for pretty much everyone in the race. But then, the researchers behind the Chinchilla paper just kind of hit the brakes. They looked at this mad dash for size and asked a really basic question. Are we actually using all this incredible computing power in the smartest way possible? Or are we just, building bigger and bigger engines without even thinking about how much fuel they need? So they framed the problem with this really precise scientific question, and I'm quoting directly from their paper here. Given a fixed flops budget, how should one trade off model size and the number of training tokens? Now, in plain English, what they're really asking is, if you have a set amount of computer power, what's the better bet? Building a bigger brain or just giving it way more books to read? So the old rule of thumb, which was based on some earlier research, was that you should always favor size. Like, if you got more computing power, you were supposed to pump up the model's parameter count way, way more than the amount of data it was trained on. But DeepMind's new analysis, it found something totally different. The most efficient way forward, what they call the compute optimal recipe, was to grow both the model size and the training data together in lockstep. It's all about balance. And this chart, wow, this chart shows you everything. You see that steep dotted black line? That's the old bigger is better path everyone was sprinting down. But these new, more balanced lines, that's the smart path, the one they figured out after training over 400 different models. They realized that the biggest models in the world were actually way off course. So this gets us to this core idea of compute optimal training. All it really means is finding that perfect sweet spot. It's about getting that ideal ratio between a model's size, its parameters, and the amount of data it learns from, its tokens. So you get the absolute best performance without wasting a single bit of computer power. It's about building intelligence through efficiency. Okay, so a new theory is great and all, but you have to prove it, right? And that brings us to the main event, the Chinchilla experiment. This is where DeepMind put their new recipe to the ultimate test. The setup here is a classic David versus Goliath story. In one corner, you have Gopher, an absolute heavyweight AI, clocking in at 280 billion parameters, trained on 300 billion tokens of text. And in the other corner, you have our challenger, Chinchilla. It's 4 times smaller, just 70 billion parameters, but it was trained on a jaw-dropping 1.4 trillion tokens of data. And here's the kicker. This is the single most important part of the whole experiment. This was a fair fight. Both models were trained using the exact same amount of computing power. This table really just lays it all out there. Look at the giants, GPT-3, Gopher, MTNLG. All of them have these massive parameter counts, but they were all fed a pretty similar diet of around 300 billion tokens. And then there's Chinchilla. Its recipe is from another planet. It just completely breaks the mold. So the stage is set. We've got 2 models, one giant, one small, both built with the exact same energy budget. The only difference was the recipe. So how did the smaller, but much better fed model actually do? Well, let's start with a really important academic test called MMLU. It measures how well a model understands 57 different subjects. And the results? It wasn't just a win, it was a knockout. The massive Gopher model, it scored 60%. Chinchilla, 67.6%. That is a huge jump in performance from a model that's 4 times smaller. And this wasn't some fluke. When you dig into the details, subject by subject, Chinchilla beat Gopher on 51 out of the 57 tasks. It didn't matter if it was law, politics, history, or philosophy. The smaller model was just consistently better. And it was the exact same story on another tough set of tests called Big Bench, which has all these tricky reasoning and creativity puzzles. Again and again, Chinchilla just came out on top, dominating its much, much larger rival across the board. The paper's conclusion really leaves no room for debate. They state that Chinchilla, and I quote, uniformly and significantly outperforms Gopher, GPT-3, Jurassic 1, and Megatron-Turing NLG. That's a clean sweep. The smaller, smarter model beat every single one of the giants. So, okay, a smaller Model 1. Big deal, right? Well, yeah, it is a massive deal. These results signaled a fundamental shift in how we should all be thinking about making AI more intelligent. So here are the big takeaways. First, this research proved that most of the huge AI models out there were, frankly, undertrained. They were like giant brains that just hadn't read enough books. Second, the real key to better performance isn't just raw size, it's the balance between size and data. Third, this basically means the future of AI is about working smarter, not just bigger. And finally, this puts a massive, massive emphasis on getting high-quality training data. Data isn't just the fuel anymore, it's a core part of the engine's design. And let's not forget the huge practical benefits here. Because Chinchilla is 4 times smaller, it is dramatically cheaper and way more energy efficient to actually run and fine-tune for real-world stuff. You get better performance at a fraction of the cost. I mean, that is a true game changer. Ultimately, what the Chinchilla paper did was declare that the simple, straightforward age of bigger is better is over. That race for just pure size has been replaced by a much more complex, much more interesting search for the perfect recipe. And that leaves us with a pretty fascinating question for the future. If it's not just about size anymore, what's going to be the next big thing that defines the cutting edge of artificial intelligence?